Questions tend to inspire a world of ideas, much more than a mere need to answer. It's the unending quest of understanding our origins, the laws of nature, and the depths of a human mind that most often leads us as far as astray, only to be found anew. My name is Naman Jain, and we welcome you to the very first episode of Zeroing In, the science podcast, brought to you by the Sounding Rocket and the IIST Alumni Association from the Indian Institute of Space Science and Technology. Over our journey, we will explore the multitudes of ideas and research being carried out by the professors and researchers in the scientific community closer home, across the country, and the world. This is Zeroing In. Welcome to today's episode of Zeroing In. I'm Naman Jain, and joining with me today as co-host is Prajwal Patnaik. Today, we are in conversation with an astrophysicist whose belief in the scientific quest for understanding the physical universe and our place in it as humankind, as he puts it, is one of the most remarkable adventures our species have ever embarked upon. This has led him to investigate the intricate mysteries of the universe very hands on. Back on Earth, he currently holds the position of an associate professor at the Indian Institute of Space Science and Technology. He pursued his master's and doctoral work in the discipline of astronomy and astrophysics from the Pennsylvania State University after a BTech in electronics and electrical engineering from CET. An avid educator and an active science communicator, he is well known in the community for his popular science columns in magazines and newspapers, public lectures, and scientific documentaries. In academia, his research work focuses on understanding the details of intergalactic medium in various scientific dimensions, including the distribution of baryonic matter therein. In our conversation with him, we discussed about his curious journey, his exciting research, and the further ideas on the field. A very warm welcome to Dr. Anand Narayanan. So, sir, we would like to begin with a discussion about the beginnings and how your formative years were as you remember them. What was the atmosphere like when you were growing up, and how was it around? Did you know somehow that this was where your passion would lead you?
Okay, so see, I grew up in a family that always valued education and the pursuit of knowledge without worrying much about the utility of it. So at home, I remember that we were always surrounded by books of all kinds. Okay, there was fiction, non-fiction, history, literature, etc. So reading was always encouraged, and whatever my parents read, they shared it with us children. So there was always very good family conversation centered around books, reading, and about all aspects of knowledge. So I think looking back, all that laid the foundation for my own interest in higher education and learning. And somewhere along the way, I think my thought process and my mind kind of matured to a level where I also started asking some meaningful questions about many things. So during my 11th and 12th, I developed a kind of interest for physics. During my BTech, I started reading general books on astrophysics. I read books by Patrick Moore, by Ken Croswell. I read books by Carl Sagan, Fred Hoyle. All of them were great communicators of science. So their writing and the ideas they put across in those books, they were very fascinating for me. And I think it left a very powerful impression on me. And above all, as you very well know, astrophysics as a discipline has this charm because it deals with some of the most profound questions that the human mind has ever bothered to ask. So naturally, I was attracted to it. And also, as I started reading more on astrophysics by myself, I realized that it was a very interesting way to understand physics because astrophysics puts physics in a very interesting context. Okay, sometimes in extreme conditions, you understand physics. So I think all that sort of drew me into that subject. So I won't say that there was any particular instance or incidents or a person who kind of influenced my interest in this discipline, but it was a cumulative of all of it, right from the upbringing that I had at home, where, as I mentioned, we were always told that what is worthwhile to pursue in life is knowledge. Okay, so that's how I became interested in thinking about a career in science, thinking about a career in astrophysics. And so there was all those things feeding into my ambition and feeding into my confidence that I will be able to pursue something like this.
Uh-huh. That's really beautiful. One of the lines that I pick up from this is that the idea of valuing knowledge was always there. And that somehow naturally transcended to your understanding that there was a career in science to be pursued.
So, we would like to ask about your decision to pursue astronomy and astrophysics after completing your undergraduate course in electrical and electronics engineering. How did the people around you react to this decision? And how was this transition for you on a personal level? And how did the atmosphere in the Pennsylvania State University shape your mind as a researcher?
Yeah, so my decision to go for higher education in astrophysics became stronger as I read more and more astrophysics during my engineering years. So you can say that I was teaching myself. So there was some kind of self initiated learning that was going on. And initially, I started reading popular books in astrophysics, but then slowly I started also reading more technical books in astrophysics. By technical books, I mean textbooks in introductory astrophysics. And so I found that the way Okay, so astrophysics is basically a way of looking at the physical universe, the world around us, and more importantly, the world above us through the prism of physics. So I developed some inside information on the kind of physics and mathematics that goes into astrophysics, and I found that I will be able to manage it even though I didn't have a firm academic foundation in physics. So I thought it's good to go into this. So when I announced this, I don't think there was any objection. As I said, I was lucky, or I was fortunate enough to be born into a family where they encouraged the thinking out of the box. So the freedom to experiment with life was crucial, and my family provided me with that. And I think that was a huge sort of strength or foundation. When I joined the graduate program, the PhD program in astronomy and astrophysics at Pennsylvania State University, so all incoming students, they are given a graduate student handbook. So it's like a user's manual on how to plan your PhD years. And the first sentence of that graduate handbook was something interesting. It said, graduate school in astrophysics is like drinking water from a fire hose. Okay, so your thirst will get quenched, but you may kill yourself in that process. Okay, that's what it meant. So it was their humorous way of saying that it's not going to be an easy ride. There's going to be a lot of demand, and surely, as I went through the months and years, I realized that that sentence was actually true. So the coursework was very demanding, and since I didn't have a thorough exposure to physics before joining that program, it was all the more challenging for me. But I taught myself physics on a need to know basis. So it was a very tough ride. It was a steep climb, but all good things in life, the climb is usually steep. The environment was highly supportive. All the faculty members who were there, they looked at every graduate student in that context in from which they came. So they never looked at the students from the same yardstick. There was always constant conversation with faculty members on where we lack and where support was required. One of the things is that in a research environment, you learn in the classroom context, but a lot of learning also happens through osmosis. Okay, so you are in an environment where everybody is thinking about new ideas, everybody is thinking about different ways of approaching a problem, and so you watch and see them perform, and then you also learn. Okay, so one can approach thinking this, one can solve problems this way, one can cope with challenges in this way. So formally and informally, one gets to learn a lot, and that's what happened during my PhD years also.
Okay, it's actually quite reassuring to know that given proper environments with some hard work, one can surely be enabled to pursue a passion of theirs. So, continuing along the same lines, we would like to delve a little onto your doctoral work. How did you get interested in quasars exactly at that point? And reading a bit through your thesis also, and how it talks about quite intimidating and interesting things, we'd like to ask you, how did that whole idea come about for you, and what did it entail? What did the work exactly entail?
Yeah. Okay, so before joining Penn State, I only had a peripheral understanding of what astrophysics is. So I wanted to choose a place where there was a large diversity in terms of research. And Penn State had people working in different areas of astrophysics. There was a huge diversity. And so, since I didn't know exactly what research in astrophysics is about, I wanted to be in a place where I could sample some of these areas and before choosing what I would want to work on for my PhD. So I was looking for a project that is a good hybrid of theory and observations. So I wanted something which is a good admixture of both these, and study of quasars and light from quasars to understand properties of diffuse gas in the universe. That seemed like a very interesting thing, and so I chose that as my work. The work that I did for my doctoral dissertation, it essentially involved using distant bright galaxies, which are generally known as quasars, to study the physical properties and chemical abundances of gas that is in between us and that quasar. So as it turns out, most of the ordinary matter, okay, which is fashionably referred to as baryonic matter, most of this ordinary matter in our universe lives outside of galaxies. So if you are actually just looking at pictures of light coming from galaxies, we are only seeing the tip of the iceberg. Okay, most of the ordinary matter is in a very diffuse form outside of galaxies in the environment surrounding galaxies. So, to study this visible component of our universe, this ordinary matter, we need to make use of a technique called absorption line spectroscopy. And this technique involves looking at very bright distant galaxies and collecting the light from those galaxies using telescopes and sending that light to a spectrograph, which disperses that light. And when you look at the spectrum of that distant galaxy, you are going to see evidence for whatever parcel of gas that is between us and that galaxy. So even if that parcel of gas is not emitting starlight, it's going to cast its spectral shadow on the light. So this is a interesting way to study diffuse gas in the universe. So my own research work was trying to understand a particular kind of parcel of gas that is present in our universe, from the present universe to the very distant universe over roughly 10 billion year history of the universe. How has this particular parcel of gas evolved over cosmic time?
Uh-huh. Okay, I mean, so there's this one thing that I really wanted to ask regarding this. There are so many specific details in this broad range of work that you just described, and I see that your thesis was also clearly pointing that out, that weak, low ionization quasars absorption line systems. So, I mean, how do you decide, or how do you point at the details that you want to explore? How do you go about that process when you are conducting your research?
Yeah, so there's this old saying about research that research is knowing more and more about less and less. Now, I think in different fields of science, the approach could be a little bit different, but at least in astronomy, this is the way it works. So before committing to a certain problem, you do some, you go through a checklist. Okay, you see whether the kind of questions that you're trying to answer, whether they are answerable with the current data that is available, or the data that is likely to become available with existing facilities. So there are a lot of questions for which you may want to know an answer. For example, we may want to know whether there is intelligent life elsewhere in the universe. Okay, but that's a question that we can live with throughout our life, but maybe we may never find an answer to it. Okay, that's an interesting question, but that's probably not a question that we should go after when we are planning for a PhD. Okay, so you go through a checklist and see whether there is enough data that is available, or whether there is enough information that's going to become available to address that particular question. And second is, what kind of tools are required to address those questions. If that is also available, then you kind of jump into it and then you go through that process. And research in any discipline, it has certain characteristics, which is that you are working in an area that probably other people have not worked a lot on. Okay, they may have worked on allied areas, but this particular question maybe nobody else has looked at in great detail. So you are on kind of on your own. You are sort of clearing the path and making your own way. So that means that it's going to be an emotional ride. So that's another thing that you prepare yourself. When you start off this journey, there are going to be moments of ecstasy and there are going to be moments of agony. But that is true for any creative process. Okay, there's a lot of ups and downs that you go through, but that's part of the package. That's what you sign up for. So this is all the things that happens to you, and this is how we get into research, and and finally with support from your own mentors, support from your own supervisors, who kind of hold your hand at times and show you the right direction, your work gets completed. So yeah, it's an interesting, it's a slightly long innings, but it's a very interesting journey.
So, as you mentioned, research is about trying to clear unexplored paths, and while pursuing a PhD, one has someone to turn to for guidance. But as an independent researcher, one is free to wander about. On that note, we would like to talk about the latter half of your journey. Your current research shows a broad range of ideas being delved into, like search for distribution patterns of baryonic matter, the use of spectroscopic data in understanding high metallicity of extragalactic gas clouds, and about the investigations of active galactic nuclei. So, would you like to throw some light on your current research directions?
Yeah. Okay, so whatever research that I'm currently doing is an extension of the kind of work that I started off during my postdoctoral years. So after my PhD, I went for my postdoctoral work at the University of Wisconsin-Madison, and it was this was in 2008, and it was a very exciting time because right around 2009 was when the last servicing mission of the Hubble Space Telescope was done. One of the main tasks that they did during the servicing mission is to install a very unique spectrograph on Hubble called the Cosmic Origins spectrograph. And so I started my work with a set of people who were part of the Cosmic Origin spectrograph team. One of the big questions in observational cosmology or extragalactic astronomy at that time was the census of baryons in the present universe. Okay. So let me explain that a little bit. It turns out throughout cosmic history, throughout the 13 billion year history of our universe, this ordinary matter has mostly lived outside of galaxies. In the very high redshift universe, in the distant faraway universe, 98% of ordinary matter lives outside of galaxies, for a simple reason that galaxies had not formed then. The universe was too young, so galaxies were just beginning to form. And then 10 billion years or 13 billion years rolled by, and many galaxies and galaxy clusters and galaxy groups formed. So you would have assumed that a lot of matter would have flown into those galaxies. But observational census of ordinary matter in the local universe showed that only 10% of the cosmic inventory of baryons are actually inside galaxies in the form of stars, planets, etc., which means 90% of it is still outside. So in other words, galaxy formation, the formation of large scale structure in the universe, is a highly inefficient process. You gave the universe 10 billion year time, but still it could form only galaxies with an efficiency of roughly 10%. So if you want to study the only observable component of our universe, which is visible matter, you need to look outside of galaxies. And so the quest began to complete the observational census of ordinary matter in the low redshift universe. And when they did this search, they found out that no matter how hard they tried to look at where these baryons could be lurking outside of galaxies, the observational census was always falling short of 100%. Okay, many observational searches were done, and they found out that the baryons outside of galaxies add another 50% or 60% to what is inside galaxies. So the census was kind of hanging at something like 60%. So 40% of the baryons were still missing. So this was termed as the missing baryons problem. Okay, obviously, because baryons are missing, so missing baryons problem. So there was a need to complete the observational census of these baryons. So one of the main science drivers for building this cosmic origin spectrograph was to complete the baryon census in the low redshift universe. So COS was installed in 2009, and data started coming in, and this observational search began. And since then, the census of baryons in the low redshift universe have come very close to 100%. So the missing baryons problem is kind of solved. So this is an area that I have been working on for the last 10 years and more. Off late, that work we have been doing also with students in IIST who have been doing projects with me, and where we try to detect where these baryons are present, at what densities and temperatures these missing baryons could be present, and what kind of astrophysical environments they are present. So that's the work. That's been most of that work. And whatever you just mentioned in the question, those are all allied topics related to this. But the grand theme is going after the baryons in the low redshift universe and trying to complete the observational census of them.
Okay. Really interesting. I mean, it actually fills up a whole broad world of questions that I have now going on. So there's this enveloping idea of trying to figure out where the missing baryons are, right? Is this all that we're trying to figure out while analyzing this data, or is there something else that also comes out of it that you find helpful? And the second part, which is perhaps more naive, is if this investigation is somehow aimed at also, maybe even very peripherally, at reconciling the seeming disconnect between the dark matter hypothesis and the elusiveness surrounding the attempts for its direct detection.
Okay, so I think I'll answer the second question first. Okay, so whenever we say missing matter, usually people confuse it with dark matter. But as you mentioned rightly in the question, these are two different things. There seems to be overwhelming evidence or observations from multiple directions seem to indicate that there is a invisible gravitating component to our universe, which is called dark matter, and there is even probably an even more mysterious component of our universe called dark energy, which is causing the expansion of the universe. So dark matter and dark energy together add up to 96% of the energy density of the universe. All the stuff that we see around us and all the stuff that we call as galaxies, stars, planets, etc., they are just 4% of the overall energy density of the universe. So what I was explaining as missing baryons is that 4%. Okay, so even in that 4% in the local universe, we don't know where most of that 4% is. The observational census of baryons in the low redshift universe, that doesn't directly address this question of what dark matter could be or what dark energy could be. Those questions are left out, but it is linked with dark matter in the following way. When we are trying to find where these baryons could be present, where they could be lurking in our universe, we take the help of numerical simulations, we take the help of theory to tell us where we should be looking. Okay, the universe is a vast place, so if any pointers on where we should be looking would be very useful. So studies of something that's been happening in cosmology over the last 20-30 years is that from a theoretical point of view, many people are simulating the formation of large scale structures with the help of supercomputers. So how galaxies, galaxy clusters, etc. form, and how did the large scale structure of the universe come about. So these simulations, they don't have to worry about missing baryons, etc., because you are simulating the universe in the computer. So you put the baryons and you can watch what is happening to them with time. And so these simulations show that in the present universe, a lot of baryons are present in highly ionized form, okay, as a plasma with temperatures of 100,000 Kelvin to a 10 million Kelvins. And this gas is at such high temperatures because of the formation of structure in the universe. These galaxies and galaxy clusters form under the influence of dark matter. So dark matter provides the scaffolding on which ordinary matter forms structures. So whenever we see a galaxy, the galaxy is actually held by the underlying potential of dark matter. So dark matter is this invisible framework within which ordinary matter is organizing itself into these large scale structures. So during the process of structure formation, when ordinary matter flows into dark matter potential wells driven by the force of gravity, the speed with which they flow exceeds the speed of sound, and that produces shocks, okay, astrophysical shocks. And these shocks tend to shock heat the matter to very high temperatures of plasma. So if it is in a completely ionized state, it's very difficult to see them in absorption against background sources, okay, because the electrons are all ripped off from the atom. So it's very difficult to see it, but one can detect it provided one has access to far ultraviolet high energy spectroscopy. Okay, so that's where, so the theory says that, so that is the kind of energy range that we should be looking at, that's the kind of spectra that we should be looking at. That's why cosmic origin spectrograph was built, and that's why it has succeeded in detecting a lot of these baryons. So the way the work is connected with dark matter is we are following the properties of matter within the framework of dark matter. That's how it is. Yeah,
Extremely fascinating.
It was really good to see how enthusiastically you spoke about it. Like even at a point you had to actually leave your mic and
use
go
both
with
my
the
hands.
flow.
Yes, yeah.
But this was extremely interesting. I mean, I never read about this. This is something that's completely left out from what we are taught in the popular culture.
So, sir, would you like to throw some light on what scientific research directions did you not pursue? Okay, maybe due to lack of time, like you didn't find time to, but you were otherwise very interested to do it.
So while I was doing my PhD, a field of research that was gaining a lot of momentum was the discovery of planets beyond the confines of our solar system, orbiting other stars. So these are called extrasolar planets. And this was an up and coming field. It was like an adventure that was unfolding in astrophysics. Okay, so 1995 is when the first extrasolar planet around a sun-like star was discovered. And Pennsylvania State University, where I was doing my PhD, had people who were part of a larger campaign to find extrasolar planets orbiting other stars. So it was a very interesting topic because this is a question that a lot of people are interested in, for the simple reason that one of the big questions that has been occupying the human mind for a very long time is the possibility of finding life elsewhere in the universe. So the first step in trying to answer that question is to find a potentially habitable, safe haven for life. Okay, and planets, life as we know it requires a planetary environment. So prior to 1995, the only example that we had of a planetary system was our own solar system, and all kinds of grand ideas about how planets form around stars were all based on this one example of our own solar system. But 1995, the first planet was discovered, and following that, more and more planetary discoveries started coming up. So I can say that planets came back to the centerfold of astrophysics, so to speak. It once again became very important, and there was a lot of interest in it. And also at that time, there was a development of an interdisciplinary field of science called astrobiology. Okay, which is a happy marriage between life sciences and astronomy and geology and atmospheric science, where you have people with expertise in all these fields trying to answer one fundamental question, which is could there be life outside of Earth? So the US Space Agency, NASA, it identified 11 institutions all across US to start astrobiology programs, and Penn State was chosen as one of the Center for Astrobiology Research. And so we had a program in our Department of Astronomy and Astrophysics where you could get a double PhD in astrophysics and PhD in astrobiology if you are working on topics related to exoplanets and allied astrobiology areas. So the double PhD was not that attractive, but what was interesting to me was that this seemed like a very, very exciting field to do something on. Okay, finding planets around other stars. It's far more easy to explain it to people what I'm doing than quasar absorption line spectroscopy. Okay, I can always say that I'm looking for planets around other stars. It's a much more sellable idea. So that's one area where I wish I had taken some time to do some work. But the universe has very interesting ways of compensating for whatever we miss out on our life. And so now I am at IIST. I'm teaching a planetary science course where I teach a lot of exoplanet research related topics. Okay, so I teach the techniques that astronomers use to detect planets around other stars. This semester I'm also teaching 7 lectures in astrobiology, which is an institute elective. So that's my way of pacifying myself for having missed out on the opportunity to work in that field.
Okay, to jump a bit and talking about the non-technical ideas, your contributions to popular science magazines as scientific articles aim at basically generating general awareness, yet probe into considerable depth without shying away, for instance, from the underlying technicalities. Is it possible to articulate in words about what you seek out for while taking up such endeavors?
Yeah. So when I was in grad school, the professors there used to say that being a good researcher is trying to cultivate a multi-dimensional vector within ourselves. So one is of course raw intelligence, okay, and not everybody is gifted with raw intelligence. Okay, some people are born with it, and if you have that raw intelligence in abundance, you are well and good. But then, in addition to having intelligence and innovativeness and thinking, etc., it's also important to be able to articulate your ideas in a manner that is coherent, comprehensible, and in a manner that's accessible to a wider cross section of people. So we were always told to think and write and talk a lot about our own work, okay, so that we become comfortable with explaining our own work. And this was not only true for education and public outreach. Even when we are giving scientific talks, scientific lectures, the professors, our mentors, always used to say that you try to make it as simple as possible. Okay, often people tend to appreciate your work not based on how much work you have done, but how well they understand your work. People's impression about your own work depends on how well they understand it. So this ability to communicate is something that our professors laid a lot of emphasis on. So writing for the general public, communicating science, these are things which I always enjoyed doing, because that's the time when I can challenge myself and see whether I can tell a story in a way that has a beginning, a middle, and an end without leaving it hanging. Writing articles for newspapers, writing articles for school magazines, making documentary films, these are all attempts to do that and to reach out to a wider cross section of people.
Sir, to conclude, I think I would like to ask this final question. Given that you engage a lot with students from all age groups, for instance, from school to college and to even graduate students, what inspires you or fascinates you most when you talk to younger children, and how does that experience contrast to when you're interacting with a graduate student? What is it that strikes you the most?
Yeah. So this is a very tough question to answer. See, I think as one of the fundamental attributes of what makes us human is curiosity. Okay. So I think one of the challenges of growing up is to keep that sense of wonderment and curiosity to the world around us alive, because that is where knowledge becomes wisdom. Okay, so we may know a lot of things inside our head, but that is knowledge. Okay, unless that becomes part of our inner being, it doesn't transform into wisdom. And these two are very different. Knowing something and realizing what it means is very different. As we grow up, okay, we have to keep on rebooting our system so that we don't lose this connection between knowledge and wisdom. The scientific worldview can be as refreshing, as entertaining, and as liberating as art or music or anything great that the humankind has done. Okay, so if only we understand it in its proper context. So this is the difference that I kind of see. To come back to your original question, this is the difference I see with small children and older students. That sense of curiosity is something that we lose out. But if you think about it, that is the hallmark of the human species. So maybe losing the sense of curiosity could also mean that we cease to become human.
This was Zeroing In with Dr. Anand Narayanan. It has been brought to you by the Sounding Rocket in collaboration with the IIST Alumni Association from the Indian Institute of Space Science and Technology. We extend our sincere gratitude to Dr. Narayanan for sharing his fascinating ideas and insights with us on behalf of our whole team, which included Fenil Shah, Manish Chauhan, Prajwal Patnaik, and Shreya Mishra, and I am Naman Jain. Thanks a lot for listening to this episode. If you have any suggestions, you can write to us on zeroingin@outlook.in or contact and follow us on our Instagram handle at zeroinginpodcast or the Sounding Rocket page on Facebook. We will see you on the other side of the week with another exciting episode of Zeroing In.